Turn to slide 4. I will introduce the example in this section, the example that will be used throughout the whole talk. Slide 5 shows the so-called grumpy or depressed data, which comes from a study of at-risk mood profiles related to depression. So these are data that are obtained by ESM questionnaires measuring positive and negative affect in Dutch adolescents. So the ages are 12 to 16 and 63% are girls. We're going to take a look at positive and negative affect, these common measures in psychology. And they're each measured as an average of 6-7 category items. We also have a third variable, tiredness, which is measured on a 7-point scale. Sample size is 240, and there are several measures per day for 7 days in a row, Tuesday through Monday. We also have some covariates that we're going to use, gender and the so-called SDQ measure, which is a measure of childhood emotional problems. You can read more about the study in this article. On slide 6 then, I point out that the ESM questionnaires were filled out throughout the day, including during school hours. And they were delivered on their smartphones. 8 measurements, well, there were supposed to be 8 measurements. We'll see it's a little bit different than that. It's supposed to be taken randomly in 3 blocks of time between 8 in the morning and 10 at night. So 1 morning measurement between 8 and 10, and 6 measurements between 10 and 8, randomly dispersed through the day. And then an evening measurement between 8 and 10. Turn to slide 7 then, section 2. How do we handle varying types of measurements that arise by these random measurement times? Slide 8, we're starting to move towards the Mplus option T interval, which is needed because times of measurements are not the same across people. Data are misaligned with respect to time due to this random measurement occasion feature. Now, of course, varying times of observations are common in longitudinal data, but it needs special attention in DSEM due to using lagged effects in DSEM. And lagged effects, by that we mean that we use in the model the time distance between the measurements at time t minus 1 and time t, needing that to be the same across people. So the distance means the same thing. Not 1 hour for one person and 3 hours for another person. And this can be accomplished by inserting missing data rows in the data set to align time. That's what the T interval option does. I'm going to show you 2 hypothetical examples and then we'll take a look at the real data. On slide 9, you have a first hypothetical case with frequent measurements. So let's take our time to look at this. First we have the original data, and then to the right we have the aligned data that we're going to use for analysis. So for the original data, we will look at 2 people, ID1 and ID2. And for each of them, we have a time measure, hours, and an outcome, which we'll just call Y. And then we look at the data rows. And for ID1, we measure that person at 9 in the morning, 10 in the morning, and 11, and at 1 in the afternoon. So we have 4 measures for that person. For the second person, however, we have measurements at 9, 11, and 12. So only 1 is common with the first person. So what we do is to align the data so that we insert a missing data row for an hour that observed data is not available. So for ID equals 2, we don't have 10 o'clock for that person. So we put missingness here. ID equals 2 is measured at 9 and 11, but not at 10, whereas 10 o'clock had a measurement for ID equals 1. Likewise, we insert missing data, these asterisks, for the hour 13, for the hour 12 for the first person, because we only observed time 11 and 13. And for the second person, we include missing data for hour 13. So quite straightforward. So the first person gets 1 missing data row and the second person gets 2 missing data rows. So this is insertion of missing data rows using a time interval of 1, which is obtained by the variable command option t interval t parenthesis 1, where t is the name of the time variable. So for instance, the hour here that we were working with. And the data row will then be what we will call a bin number, the time that's actually used in the analysis, this integer time, 1, 2, 3, 4, 5. On slide 10, we have a second hypothetical case, in this case, infrequent measurements. So with infrequent measurements, time interval 1 would give many missing data rows. So if you look at this original data set here, we observe somebody at the hour of 9, 13, 16, 19, and 21. So with 1 hour time interval, we would have missing data rows for 10 o'clock, 11, and 12, and then 14 and 15, and then 17 and 18, and then 20. So that would be quite a few missing data rows. If instead we use a wider time interval, like 2, we have the bin range from 9 to 10 here. We have somebody in that bin, and this person. 11 to 12, we don't have anybody, so we have missing. 13 to 14, we have this 13 person, and 15 to 16, we have somebody. 17 to 18, we don't have anybody. And 19 to 20 and 21 to 22, we have an observation. So here we would end up with only 2 missing data rows as opposed to many by inserting all of the missing hours under the time interval 1 situation. Now for the grumpy or depressed data on slide 11, let's take a look at that. So the total number of hours for this study is 24 hours times 7 days, 168. Now the smaller the time interval, the better the match to the data, but the more missing data is inserted. So here we have for this data set, I think we have 3 candidates for time interval. Time interval 1, time interval 2, and 3. If you choose 1, then we get 24 time points per day, 1 for each hour. Maximum number of time points will be 168. And the coverage then is 0.17, coverage being the proportion not missing. So fairly low coverage. Can handle it, but for some more complex models, that's going to give problems. Time interval 2 gives 12 hours per day, 12 time points. Maximum number of time points then is 84, coverage 0.341. Much better coverage. Time interval 3 gives 8 time points per day, which was actually the aim of the study. Maximum number of time points then is 56 with coverage 0.507. Usually we want much more coverage when we analyze data, but in this case low coverage works fine, except perhaps when it goes down to very low values. So now let's look at the real example here. A person number 41, and let's consider time interval 3, so 3 hours. So you have then, starting with the bin range 0 to 2 here, so this is after midnight. So the bin range is 3 here, 0, 1, 2. And the midpoint is then, since the bin range is 3, midpoint is 1.5. And if you add 1.5 to 0, you get 1.5. So that's the new time midpoint of the bin range, which we're going to use not for the analysis, but to gauge how misaligned the data is. Now, if you take a look at the observed time 7 and 8 in the morning, we have the bin range 6 to 8, and it falls in, so 2 time points that are observed are falling into one and the same bin range. And we don't want that. We don't want several people in the same bin. So you spread them out in Mplus. You don't. If you take the average, you would get a change in the precision of the measurements, which is not something you want. So we put 7 into an earlier bin and keep 8 in the same bin. So you get a slight misalignment there. The midpoint is 4.5 here for that bin, and we're saying, so that's between 4 and 5 in the morning, and we give the 7 o'clock measurement, see that as an earlier measurement. So some misalignment there. Now look at 12 and 14. Here we have to do a more elaborate scheme. We have to move 14 down to the next bin and then move 16 and 18 further forward. This is all happening because we have a very wide time interval of 3 here. Perhaps not desirable for this person. So for this person who was observed at time 18, 6 in the evening, and that person gets misaligned to fall into the bin range 21 to 23. So about 10 o'clock at night. So the distance here then with the which is used to gauge the misalignment issue is 4.5 for that person. And we have information in the plot output about this kind of misalignment per person and overall across persons for different time interval choices. So you have to decide yourself from a substantive point of view, is this an important deviation? How you feel positive affect or negative affect at 6. Does that distort the picture if you pretend that that happens at 10 in the evening? Or is that not important? And also to see how often does it happen? How many people does it happen for? Perhaps it's ignorable because of that. Now, and you can continue to the next day's morning here, 7, 8 in the morning, and we have to move one person into an earlier category. 2 things here, technical. The range is more precisely stated as from 21, greater than or equal to 21 to 24. I'm looking at this here, this range. 21 to 23 is what we say, but it's more correct to say 21 to 24, where 24 is not included, when time is not even hours, when there's fractional time. That would be a more precise way of stating it. And the principle is, again, if there's more than one observed time per bin, rearranged observed time into neighboring bins. One move due to bin 3, up here, that's one move, and 3 moves due to bin 5. Bin 5 moves 14, which then moves 16 and 18 as well. And so 4 out of 8 observed times are misaligned in the first day for person 41. 7, 14, 16, and 18. So there's something for you to sit and think about. And misalignment quantification is this SMSE measure, square root of mean squared error, simply the distance in hours. Now, let's take the same person, but time interval 2. So a smaller time interval. And for the bin range, we only have one observed time for each and every bin range. Perfect alignment, no need to rearrange observed time. So there, it doesn't hurt the data at all. But if you go to, that was person 41, if you go to slide 14 and person 20, then you will have, with that same time interval 2, you will have 2 measurements falling into one bin, and you have to move the one measurement to an earlier empty slot, so 1 misalignment. Now, for day 2, then you would have 2 misalignments. You have to move twice here. You have to move 36 up to earlier, 38 into 36's former position, and keep 39 in the same spot. So this gives you a flavor of what Mplus does for different time intervals, and perhaps also ideas for how you might want to manually score your time to align to synchronize people's times. Maybe your manually aligned time does a better job than what Mplus automatically does, but as we will see in analysis to come, in 2 places I have compared the results when using T interval 1, 2, and 3, and there are not important differences.